Hello, my name is Pablo Vaquero, and today I will talk about my project in the Urban Forge. So the contents will be divided in four parts. First, we will begin with the design of a megacity skyscrapers with coastal winds. Then I will talk about solar power grids and scorching deserts. And the last project will be about underwater tunnels and ocean depths. And finally, I will talk about the innovation I introduced in each of these projects. Okay, so we will begin by talking about megacity skyscrapers and coastal winds. So the first thing we need to take into account is the material to be used. I chose titanium zirconium alloy. The choice of titanium was due to its great mechanical properties. For instance, high Young's modulus, tensile strength, as well as toughness and good ductility. Um, the fact of choosing zirconium was due to its resistance to corrosion. We know that in coastal zones, the presence of salts and other particles may alter the chemical stability of these materials. So having an alloy that is able to resist corrosion is really important. Regarding its phase diagram, we can see here the titanium and zirconium. We see that it is divided into three different phases, solid alpha, solid beta, and liquid phase. It's a bit different to those studied in class, but the mechanics are the same. The way of functioning is the same. As we can see here in the lever rule, in this case its composition is quite simple. For example, I chose this point here at around 1500 Kelvin. We can see that the composition of zirconium is 60%, composition of titanium is the other 40%, and all of it is in solid beta phase. Now regarding the strength and ductility versus its composition, I'll be talking all the time. In this graph is a double graph. The left axis stands for the strength, the tensile strength in megapascals, while the right axis would represent the elongation in a percentage, that is its ductility. So we can see how at a approximate number of 20% zirconium, 80% titanium, the material achieves its maximum tensile strength and its minimum ductility, and this is the point in which we will like to work. We like to, I mean, it's a relatively good elongation, so we would like to maximize as much as possible its tensile and compression strengths. Then, talking about its microscopic analysis and surface treatments, we can first begin by analyzing its microstructure. As you can remember, at room temperature, the composition was an alpha phase. I forgot this here. I represented this as a BCC structure. And then through when temperature increases, this will cause a change in the structure of the materials, even though the percentage of zirconium and titanium will be fixed, would be of 20%, for instance, of zirconium, 80% of titanium, which was the ideal point. But when increasing temperature, we will move to 100% of beta phase, and this rearrangement in the atoms would be mainly caused by this interstitial substitution. Once we have analyzed its microstructure, we want our material to be as strong as possible and to have the better mechanical properties. And this is a good way to get this is by introducing a surface treatment, a heat treatment that is called. It's a succession of quenching and tempering. Quenching consists of raising your material temperature to really high temperatures and then decreasing it drastically with a really high slope so that you are able to form martensite, which is a very strong type of microstructure. And then you should leave it either at room temperature or control not really high temperature to perform tempering, which is basically introduced to have a uniform properties over the material. Okay, so once we've talked about those skyscrapers and coastal wings, now we're going to talk about solar power grids and scorching deserts. So the alloy I decided to use was the copper nickel alloy. Basically, as we're in the desert, we want a high resistance to high temperatures, and also due to the fact of sand and other particles, we want a good resistance to erosion. Finally, as we want solar powered grids, we would like it to be thermally conductive, and this would be achieved by having a uniform microstructure, which will be discussed later. The diagram of this alloy is really similar to the one that was discussed in class. We have a solid alpha phase, then a liquid phase at high temperatures, and in between we've got this region in which both liquid and alpha solid phase coexist. So talking now about the lever rule, in this case we can see a more complex example than before. I chose this point, for instance, right here, which I called as 70%, just for for the example. So if we want to calculate the concentration here of this material in liquid and alpha, firstly, we do know that the concentration of the material would be 70% in nickel and a 30% in copper. We don't know in what phase, but we know this only just by knowing this point right here. Then we know, if we move right here, that the concentration of liquid, which I denote by Cl, would be equal to a 53%. These numbers are made up, okay, that's for the example. And the concentration of alpha would be 85%, as I wrote there. So then if we want to calculate the weight fraction, for instance, the weight fraction of liquid, what we will need to do is to take this segment right here and divide it by the overall segment. So we just take the length of the green segment, which would be something like 85 minus 70, and we will divide this by the total length of the blue segment, which is 85 minus 53. And when performing this radio, we will calculate the amount of the weight fraction of liquid in this alloy. Then we can talk about the strength and ductility of this component. Similarly, I expressed to the previous case, I expressed the tensile strength in the left, the ductility in the right, and now we see again that the point of maximum tensile strength and minimum ductility coincides in here at around of 60%. In this case, we do not really care too much, I think, about whether it supports great loads or whether it is very ductile. So anywhere in an acceptable range, not in the extremes, would be a good choice. Okay, so now we will go to the microscopic analysis and the surface treatment. So if you remember, at root temperature, we started with a solid with 100% of alpha phase, and then as we increased temperature, we moved into a division of phases. Now it's not a crystal anymore because we introduced that liquid phase. So we will have liquid, which is in blue, and some solid particles. And it is not crystalline anymore. If we kept increasing this temperature, we would reach to a state in which all the liquid is present, but of course that is not desirable for our applications. The surface treatments or heat treatments to be considered, I think annealing is a great option. As we want the good conduction of heat through our material, we want uniform properties, and annealing is great for this task. Annealing consists basically in increasing your material temperature up to relatively high temperatures, and then reducing its temperature at a low rate. Not as Kenshin. Okay, Kenshin was something like this, really great slope. If we want normalizing, would be an intermediate one, but to have those properties, we would like to perform some annealing. Finally, I also think that a coating would be great, coated against the erosion mentioned before, as even though the materials selected have a good corrosion resistance, the particles in the desert can be highly damaging. Okay, so the last one, the last project to comment is the underwater tunnels and ocean depths. So basically, we would like high resistance to corrosion, principally oxidation, as it will be in contact with water all the time. And also we need to have a good resistance to stress, because as you know, if we've got any surface that is surrounded by water, the water will submit our component to some perpendicular forces, to some perpendicular pressure. That is why I decided to use this aluminum silicon alloy, which again, it has a great resistance to corrosion and oxidation, and it also has a high specific stress resistance due to its low density. Its phase diagram is a bit more complex than the ones commented before. In this case, we have different phases. Here we have the alpha phase, liquid phase, and this would be silicon. Okay, this line right here. And we've got those intermediate phases like alpha plus liquid, liquid plus silicon, and finally alpha plus silicon. This would be a totally solid phase, as well as this one, which is also solid. This one is also solid, and this would be all liquid, and this would be, these two would be a mixture of both. In this case, to calculate the concentrations, we can do as before. I wrote here, this is my example, okay, at a 7.5% of silicon. So we know the silicon concentration would be a 7.5%. We know then that the aluminum concentration would be 92.5%. And now we know this point here, which corresponds to the concentration of alpha. It's going to be a 5%, while the composition or the concentration of liquid in this case would be at 10%. So if we want to express the weight fraction, for example, of, let us say, liquid in this case, we just had to divide this green section that I'm drawing over here, this one, over the whole length that I will draw in purple over this length. So this will be similar to 7.5 minus 5 over 10 minus 5. And that would be the percentage of liquid percent. Okay, now regarding the strength and ductility versus the composition, I first need to highlight that the objective concentration that I forgot to mention before in the diagram, which was basically the point in which this point right here, the point in which liquid coexisted with this alpha plus silicon stage. It was at a concentration of approximately 12.7%. And this is the concentration at which the maximum tensile strength and minimum ductility occur, which was to be expected as is the most important point in the phase diagram. Okay, so now regarding the microscopic analysis of this compound, I will analyze it at a concentration of 12.7%, which is the objective concentration, as I think that the behavior is crucial. We will start by a crystalline structure in which we only have that alpha plus silicon stage. The aluminum is represented in the edges in a PCC structure. That may be another one, but I decided to choose this one. It could also be a simple cube or an FCC depending on the material. And the silicon, which is the rest of the material. Then as we increase temperature and we reach the epileptic temperature, we have now a structure that is these tiny concentrations here, tiny circles which begin to form. And if we keep increasing the temperature, as we just saw, we would end up having liquid with both components at the same concentration, at silicon concentration of 12.7% of silicon, and the other percentage is of aluminum. But the important thing right here is to understand that how the eutectic microstructure behaves differently to the other two, in which the best mechanical properties will be achieved as discussed previously. Some surface treatments to be taken into account would be nitriding and cold working. The choice of nitriding would be to prevent corrosion of water, which I think is crucial in this case. And then cold working would increase a lot the mechanical properties in a certain direction. So for example, if we want our material to be resistant to forces applied perpendicularly to its surface, we can, with cold working, align those fibers so that mechanical properties are improved. Finally, summarizing, the innovation I introduced basically was the resistance to wind and seismic activity, thanks to that quenching, tempering, and also the selection of titanium zirconium alloy. Then the temperature resistance of all materials, as it can be seen in the graphs At room temperature, they are totally stable. They are single phase at room temperature, which is the point of operation of these constructions. Then it also has a great underwater pressure resistance, thanks to cold hardening orientation, which I discussed before. And finally, I think that in all of the structures, corrosion and erosion was a fundamental point that was tackled differently, from the selection of zirconium to the coatings in the nickel copper alloy, and and finally the nitriding in the last case. So thank you very much for your attention, and that's it.